or how can we find those domains, how can we sketch those domains in the two-dimensional plane. So we were dealing with those, but today we are going to do partial derivatives. You know that the derivative of a single variable function, the derivative of a normal function, the function that the function of the kind that we considered last semester, the derivative actually gives us the slope of the function. In other words, it shows us the steepness of this function. And generally, for a single variable function, the value of the gradient was the derivative, actually the derivative of the function at the specific point x0, and that was the tangent of the angle. The tangent line actually forms with the positive x-axis. This was something for the simple functions. And if you think the functions we were working with last semester were simple, then you will have some more so simple, perhaps. So how can we explain derivative of or the derivatives of a two-variable function, or actually even what do we mean by the slope of a two-variable function? What happens there? We can't consider the derivative, a single derivative of this two-variable function. We consider derivatives by the variables x and y, in the x direction and in the y direction. Let me remind you, the graph of a two-variable function is some kind of surface. Well, it might be something more complicated than a simple surface, but if we talk about continuous functions, and functions without gaps, without emptiness in any way, we can talk about the graph of a two-variable function as a surface, some kind of surface. So if the surface is curved and if it changes direction, like the surface of the Earth or the sea with waves, for example, then we understand that this surface also has different kinds of gradients. And if you consider some kind of mountain or a hill, then the gradient of the mountain could be quite slow in looking from one direction. Like, for example, looking from the south northwards, we would see the gradient from the direction from the west to east or east to west is quite small. It's quite shallow. On the other hand, if we stood there looking in the western direction, for example, from east to west or from west to east, we would see perhaps that this mountain ridge has quite a steep gradient if we look at it in another direction. So basically the general idea is then, of course, this would be the steeper gradient and this would be the slower gradient, and we can more or less imagine what kind of surface this hill might have. So it's sort of longish, elongated, and it might be steeper from looking from one side, and then it might be less steep looking from another side, and therefore when we deal with two-variable functions, we look at two derivatives. We look at the derivatives going in the let's say in the x direction. In the x direction, the derivative in the x direction. For example, we could imagine the direction south-north is the x direction, for example. So perhaps the steepness is 1 in this direction, and then when we go perpendicular to that, in the y direction, the steepness, the slope might be something completely different. Basically, there is a possibility to look at the gradients not only in the x direction, not only in the y direction, but in any direction. Technically, it is possible. Mathematically, it is a little bit messy. So we will only consider derivatives in the direction of x, in the direction of y. So if we look at let's say cross-sections of these surfaces, looking from one side, looking from another side, then obviously if I look in the, for example, let's suppose now this let's suppose this is the y-axis and this is the x-axis, right? And this is the z-axis that shows actually the height. So if I go in this direction and the actual cross-section in the x direction is something like this, I would say that obviously when we derive by x, the gradient values would be somewhat high, somewhat steep. If I derive in the y direction, if I look like this, derive by y in this direction, then I can see that the gradient is less. The change is slower, so it makes sense to consider derivatives in various directions because the surface is not uniform in all directions. It doesn't behave the same way in all directions. If you have, well, obviously all of you have flown, and if you have flown over the sea, you might see sometimes in windy time or when there are waves in the sea or in the ocean, you can see the surface of the sea. So you can imagine what a function, what a graph of this function in two variables might look like. And obviously in one direction it changes differently from the change in the other direction. And that's what we mean by looking at partial derivatives. Partial derivatives means we are not deriving the whole thing, we are not looking at the whole surface. We are only looking at, for example, the cross sections, let's say in the x direction. That would give us the partial derivative if only looking like this, watching the x change, the change with respect to x, like this. So we could imagine the xz plane, and we could look at, we could actually look at all kinds of cross sections parallel to this plane, like this, and the derivatives with respect to x, so we only derive by the variable x, will tell us what the change of this function in the x direction is. And similarly, we could deal with the changes in the y direction. And then somehow we have to learn to put all this together to get a better idea of what the surface looks like we did with the simple graphs in one variable. That was easy. All we had to do was consider the gradient at each point, at each value of x, the steepness, and we had an idea of how the graph behaves, how the function behaves. With two variable functions, of course it's more complicated. Of course it's more complicated. And as in a single variable case, we were looking at the tangent lines. In a two-variable function, when we deal with a surface, we are looking at tangent planes. Tangent planes, like taking a ball or some kind of surface and then looking at tangent planes, at planes that are actually touching on that surface. They play the role of tangent lines in one-variable functions. Now, to deal with these, so we consider the partial derivative in a very similar way to the derivative of the function in one variable. We also look at the limit, the change of the function, if we make a small change in the x variable. Remember that the derivative of a function in one variable was the limit of the change of the function divided by the change of the variable. When this change of the variable becomes very, very small. That was the definition of the derivative in one variable functions. Now we do a very similar thing. So let's suppose that z is the function f depending on the two variables x and y. And let's suppose that we can't explore the whole surface at once. But remember how I compared this exploration last semester. I said we stand at x0, then we take a tiny step, delta x outside, and we look what happens to the function when I just make a tiny step outside, out of my starting point. So in a similar way, imagine I'm standing in this pavilion. The floor of the pavilion is the domain of the function, xy pairs, and the height of the roof of that pavilion, the height of the ceiling, is the value of my function z. And I'm doing the same thing. I'm not stepping out of my starting point in any random manner. I decided, first of all, let's explore what happens in the x direction. I step out in the x direction, look upwards, see the change in the function. So this means that I could take the change of the function in the x direction with respect to the corresponding step in the x direction. And of course we take the limit, just as we did, that delta x tends to 0, and we call this the derivative by the variable x, the partial derivative in terms of x. Which basically means that the value of y, in this case, is considered to be a constant. We can't ignore y values because depending on the y values, the function value might change. But when we derive by x, we pretend that y is a constant and that x is the only thing that changes, because basically if I step in the x direction, I'm stepping along the line parallel to the x-axis, which means my y value actually at that moment remains constant. If I only step out of my starting point, okay, let's suppose we have this x direction, y direction, domain, my starting point, x0, y0. So if I only want to explore the change with respect to delta x, I only step out in the x direction. So y, actually at this point, y remains constant. That is the reason why we pretend that when we derive by the variable x, we pretend that at that moment y is a constant. It doesn't change. So we only look at y. At the beginning it's a bit difficult. You get confused with the two variables and which are the constants and which is the one by which we are by which we are differentiating. It can be a bit messy. Another notation is, remember that in one variable, when we had the y derivative, we also could write it like this. That was because of the function differential. Differential of the function is dy. And the notation for derivatives could be like this. dy, differential of function, divided by dx, the differential of x, which is basically the same as delta x. In this case, simply to distinguish, to understand that we are talking about a partial derivative. There are more than one variables, but we are talking about a partial derivative, not the one and only derivative, the full derivative in one variable case. It was the one and only and complete derivative. In this case, it's partial. It's only in part. We are only looking in the x direction. So the notation is delta y over dy over dx. And that's actually considered the Gothic D. So it's still pronounced dy over dx, but the symbol is different simply to distinguish from this. We use this when we talk about one variable functions and normal derivatives, and in the case of two variable functions or three variable functions or more, we use this notation simply to state that it's the partial derivative. It's not the complete derivative because such does not exist at all. We can only look at the derivatives in specific directions. And similarly, we can take this function derived by the variable y, which would mean that delta y tends to 0, the corresponding change of the function if we make the change in y, when we make a change only in the y direction. So when I have explored the change in the x direction, I say, okay, it's quite steep. Then I might turn 90 degrees and start thinking, so what happens if I go this way? It might be something else. So delta y and it was delta dz, sorry. And this is dz by dy. Derivative in terms of y, and in this situation we simply pretend that x is a constant. Now, just to have a look at a couple of examples. For instance, if z is the function x cubed y plus 3y squared minus 5xy plus 8, for example. Now, if I want to derive this function by x, I will pretend that y is a constant at this moment. So the derivative in terms of y, the partial derivative by y. So if we use this notation, we write the name of the variable by which we are deriving as an index. Well, actually, it's more reasonable to start with x. More reasonable to start with x. So the derivative in the direction of x is, if y is a constant, then we have to derive x cubed. So it will be 3x squared, but y is a constant. It's like 5 times 3x cubed. So we still keep the constant factor, in this case y, pretends to be a constant. Therefore, if it is simply a factor, it stays as it was. In next case, this is a constant with respect to x. It's like a constant, there's no x involved there. So the derivative of constant is 0. So the derivative of this by x is 0. Because for x, it's a constant. Now this, derived by x, minus 5y, minus 5y, I'm reminding you, y is a constant. We pretend that it's a number. So we have number times x, constant times x. The derivative is simply that constant. And then it is a constant, so this is the derivative in terms of x. Now the partial derivative in terms of y, here we have x cubed times y.
X cubed.
It's just x cubed because this is like a constant for us. Now this pure y, so 6y, this
5x
minus 5x, and this is a 0 because that's a constant again. So then I find that the most difficult part is not to get confused with the variables. To separate, somehow you need to learn to separate in your mind when we are looking at x as a variable and y as a constant, and when we are looking at y as a variable and x as a constant. And then, of course, with respect to... Sorry.
Gesundheit.
I'm telling the truth. Sometimes the function might be very, very different when we look at it from the aspect of x and from the aspect of y. Completely different kinds of functions and completely different derivatives. So what you need to do if you have forgotten derivatives, you need to find your old handout papers, the tables of basic derivatives, and even composite functions, and look up the derivatives of elementary functions, because we need them. Okay, now the second example is one that I also love. The second example is z is 1 over arc tangent of x over y. Looks nice. It's a composite function, if you like. Let's have a look. We derive it by x, partial derivative by x first. So this is actually arctangent to the power minus 1. So I can rewrite this as arctangent to the power minus 1 of x over y. So it's a composite function, arctangent taken to the power minus 1. So first thing, remember the chain rule? Or have you forgotten it completely? Yes, forgotten. Okay, that's bad, I would say. So, the first thing is, this is the outer function. This is the outer leaf of that cabbage. So first we have to derive the power minus 1. The derivative of the power minus 1 means the exponent becomes the coefficient, and then we have arctangent to the power now minus 2, yes. Because we have to subtract 1 from the exponent when we derive a power. It's because x to the power a derived is a x to the power a minus 1. If a is minus 1, then this is what we get. Instead of x though, we have the function arctangent. Now, multiplied by the next leaf, when we have peeled off the first leaf of the cabbage, the power, we have arctangent. The derivative of arctangent, 1 over 1 plus this squared. Normally it would have been x squared, but in this case it's x over y squared, times, finally, the central part, the inner part, is x over y. We have to derive this. Now, careful, because this time we have to look at, we have to derive by x. So we pretend that y is a constant, 1 over 1. So times 1 over 1. Now we can, of course, simplify it. We get minus 1 divided by arctangent squared of x over y. Now if I multiply
But
by
that
this,
must be just simple y, because it is y over 1 over y, and then it becomes
well, actually, I would multiply by y again. So if I multiply by y squared, if I multiply this by y squared, the denominator, not by just y, but by y squared, I will get y squared plus x squared. If I multiply this by y squared. But because I only have y, but I want to multiply by y squared, I have to multiply by extra y up there. Like this, because 1 over y is the same as y over y squared. Why do I want y squared? I want to get rid of this denominator. I don't want this fraction there. I don't want this quotient. I want a decent expression. I want a polynomial there. So instead of multiplying by y, I want to multiply by y squared because I see a square here. So I think of 1 over y as this. And therefore, I get y here, and I get y squared plus x squared there. That's one partial derivative. We have got another one to make. That's a bit of work, as you can see. That's a bit of work involved there. Now, to derive the same function by y, again, first we have to derive the power minus 1. It's the same. The outer derivative is the same, so we should still have minus 1 over arctangent squared of x over y. That's this first part, times, now the derivative of arctangent, again, the same as it was, 1 over 1 plus x over y squared, times, now, the derivative of x over y, but derived by y. So x is a constant, multiplied by x.
Minus x squared.
Yes.
So
what we have is a constant x times 1 over y. How do we derive 1 over y?
Y power of
minus, you put up.
Okay, 1
minus
over
1.
y derived is minus 1 over y squared. Similar to what we did with arctangent here. It's the same thing. We derive the power y to the power minus 1. Y to the power minus 1. If we derive y to the power minus 1, we get minus 1 times y to the power minus 2, which is this. Which means I still have minus and I have y squared. And then I have x as a constant. And now we see something quite interesting. It's very similar to that derivative, this function. So it's now minus 1 times minus x is just x. It's still arctangent squared of x over y. And if I multiply these, I get y squared plus x squared. At the moment, I don't see any need to write these alphabetically. X squared plus y squared plus x squared, what's the difference? So if we compare the two derivatives, they are quite similar in a way. They are almost symmetrical, but not quite. Almost symmetrical, but not quite.
There's no minus.
No minus, right. And of course, x over y, it doesn't actually change to y over x. But in a way, they are quite similar. So some functions are actually quite surprising. In some functions, you see an interesting symmetry, an interesting pattern with respect to x and y derivatives. And in other functions, you see the derivatives don't look alike at all, they don't seem connected at all. Okay, so these are explicit functions. A function is called explicit or open or defined openly when it is written, it can be written in the form, the dependent variable z is written as can be expressed in terms of x and y. It can be expressed as an expression involving x and y and probably operations, numbers and so on. So this is an explicitly defined function or explicit function. An explicit function. Explicit means open. Open for everybody to see. In other words, I can't write, this is an explicit function because we see how z is defined in terms of x and y. This is an explicit function because we can actually see how z is defined in terms of x and y. It's defined directly. If we are given x and y, we can find z directly. Sometimes, though, we have unpleasant expressions from which, sometimes even in one variable, it is impossible to get out the dependent variable. It's impossible to untangle sometimes. In the case of one variable, non-explicit function, we could think, for example, of a function e to the power y plus x squared minus xy equals 3y squared, for example. This is not an explicit function because we cannot detangle y. It's impossible basically to express y as simply an expression in terms of x. It's too complicated, it's too messy. So this kind of function is implicit, or basically we define a function as implicit if we have some expression involving x, y, and z, x, y, z, equal to 0, but z is still dependent on x and y. So it doesn't matter that the expression is quite messy, tangled, and complicated. We still think of z as the dependent variable, the variable that depends on the values of x and y. It's simply that they are so tangled that it's difficult to write explicitly z equals something, something, something in terms of x and y. It doesn't necessarily mean that z is not dependent on x and y. So this is an implicit function. Implicit function meaning defined in some obscure, hidden way. It implies the connection. It implies the dependence of x in terms of dependence of z on the variables x and y. Don't forget to do the exercises. So implies, implicit means it implies the way in which z depends on x and y, but it doesn't state it openly. It doesn't state it openly. It's like it's giving us a hint, an implication. It implies, it's a hint. It's hinting at the connection between z and x and y, but it's not showing it explicitly. It's not showing how exactly z can be calculated if given the values of x and y. The expression is too tangled. And in the case of implicit function, we can still think that z depends on x and y, and we can still find the derivatives of z by x and z by y, the partial derivatives. But what we do is, first of all, we find three derivatives of this expression. We derive this in terms of x, partial derivative by x. So we do the partial derivative by x of this expression, the whole complicated expression in three variables this time. We derive it in terms of x, meaning we pretend that y and z are constant. We find the derivative in terms of y while pretending that x and z are constant, and we find the derivative in terms of z while pretending that x and y are constant, and then the derivative of the variable z by x, the partial derivative by x, can be expressed as minus f derivative by x over f derivative by z. And the partial derivative by y is minus f derivative by y over f derivative by z again. Again, the mathematical proof would take, too much time, and we are short of time. We have to move on. You have more practical needs than theoretical needs. We can use, by the way, we can use the same approach if we need to do a function in one variable. If we only have f of x and y, an implicit function y depending on x, we do it in a similar way. We can do the derivative of y in terms of x in a similar manner. So let's have an example of an implicit function, the derivative of an implicit function. All right. So my example looks like z cubed plus 3xyz minus 8 equals xy squared plus x squared y. What a horrible function. So first of all, we need to change this. It's an implicit function because you see z cubed and z, it would be very, very, very difficult to express z explicitly, openly, in terms of x and y. Z equals some expression of x and y. It would be very, very difficult, although there exist formulas for solving cubic equations. They are too messy and dependent on too many special cases and transformations, so better not try. So we change everything so that we get an expression equal to 0. In this case, z cubed plus 3xyz minus 8 minus xy squared minus x squared y equals 0. So now this can be considered our f expression. So this is actually the expression f in terms of x, y, z. Now we have this function written precisely implicitly, and we don't have to solve the equation for z. What we do is we find the three partial derivatives, now three of them, by x, by y, and by z. So the derivative by x, if this is a constant, 0, this by x, 3yz, this 0, this by x, minus y squared, this by x, 2xy, don't forget the correct signs, okay? The derivative, partial derivative by y, again, z cubed, constant, derivative 0.
Like a number.
This by y, 3xz, this 0, this by y,
minus
2xy, this by y is minus x squared. And finally by z, even though z is the function itself, z is dependent on x and y, we can still do technically, formally, exactly the same thing. So 3z squared plus 3xy this time, 0, 0, 0. Okay, there you go. So now the derivative of this function by x is minus, don't forget the minus in front, the derivative by f, so it's 3yz minus y squared minus 2xy divided by f derived by z, so 3z squared plus 3xy. If you like, you may take this minus sign and bring it into the numerator, for example, but you don't have to. You can leave it outside. If you don't have to do any more transformations and changes, then this is quite fine. This is alright. And by y, again, minus 3xz, this time we take this, minus 2xy minus x squared divided by 3z squared plus 3xy. If we need the particular values, if we want to know how much exactly is the derivative at a particular point, so remember that at any particular point on the surface, it has 3 coordinates, x, y, z. If we put these 3 coordinates into this equation, then we should get 0, of course. If that point belongs to the surface, its coordinates satisfy this equation, of course. Now, if we know at which point we want to find the partial derivatives, the gradients, we could take the point from the surface, x, y, z, 3 coordinates, put them in here and there, and we would see what the gradient is in the x direction and what the gradient is in the y direction. And then if we put them together, thinking in vector terms, we have a plane defined actually. We have a tangent plane. So this shows the tangent line in one direction from that point. This shows the gradient of the tangent line in the perpendicular direction. And taken together, these 2 tangent lines actually define the tangent plane to that surface. So basically these partial derivatives have a geometrical meaning, just like the simple derivative of the one variable function had the geometric meaning, showing the slope. Showing the slope of the graph. So here we have 2 slopes, one going north-south, the other slope going east-west, and then when we put them together, we get the slope, the total slope of the tangent plane. So that's the general idea behind these partial derivatives. That's why we consider them, and that's how they make physical sense. Otherwise, it's simply some abstract thing that we do, some mathematical algebraic manipulation which makes no sense. But of course, it has some specific meaning. All right, exercises. Find the partial derivatives of the given functions. We have, quite a lot of time. So which one should we? 4. I think we should start with 2. I think we should start with 2. U to the power of v. And u and v are the independent variables. I think that's critical because I've seen people messing up because they have forgotten the derivatives. First of all, I want to remind you of derivatives. How do we derive the function x to the power a, and how do we derive the function a to the power x? It's important. If we have the second, in the first exercise, function number 2, z depends on uv as u to the power v. Now we see that if we take u for the variable and z for a constant, then we have this situation. If we take u for a constant and v for a variable, then we have this situation. The derivatives are completely different. Now try to remember them. X to the power y derived.
It's 8x.
ax to the power a minus 1. A to the power x derived.
It's
ln.
A to the power x, ln A.
Yes, right. So you see they will be completely different. So now z derived by u, partial derivative by u. U is variable, v is constant. That will be this case. That will be this case. Variable in the base. Variable is the base. And constant is the exponent.
The u.
So it would be v u to the power v minus 1.
Yeah.
But if we want to find the second one, the partial derivative by v, now we have v is a variable, base is the constant. Base is constant, variable in the exponent. So we have the same u to the power v times ln of which?
Of u.
ln of u, ln of base. So now you see they are completely different. And we have to be very careful with this kind of function when we have power where both are variables, x to the power y, u to the power v, and so on. We have to be very careful in this case. So this is something that you have to remember. They are completely different functions. They behave differently. The derivatives are different, and so on and so on. Try not to confuse them. It's a typical mistake. Mostly the mistake of carelessness or forgetfulness or something. Now, if you want, now we can consider 4 or 1 or whatever. So whatever are we going to consider now? Obviously, it's impossible for me to do everything on the board right now for you.
This to the
No
power.
matter how much I would like it, and I don't.
Maybe
It will
the.
be impossible. Of course, the numbers, I think that the complication is enhanced because we see those numbers. Imagine how many functions were there in that book where I took these from.
For example, can we do 1861? Right here.
We are doing exercise 1 at the moment.
Ah,
Is
one.
there anything from exercise 1? Anything else that you need to consider? So, number 4. Okay, number 4. So number 4 is f of h and l. Yes, there are two problems with number 4. First of all, it's a quotient. So we will need the quotient rule for deriving it. Secondly, the problem is that h and l, we are used to thinking in terms of x and y, and now all kinds of variables. But those who study physics and engineering are used to all kinds of variable names. R's and T and V and rho and whatever. M, R, capital, whatever. So, if we want to derive this by h or by l, first of all we have to remember that this is a quotient, so we will need the quotient rule. We will need the quotient rule. Remember, u prime v minus u v prime divided by v squared. The derivative of a quotient. Secondly, of course, we have to remember that when we derive by one variable, the other will be considered constant. So, alright, the derivative by h. Let's see. So, the denominator is squared. So, L minus 3h squared, of course. Now, u derivative times v. U is this. The derivative by h, 2l, times simply v, which is L minus 3h, minus u is not changed to hl, times v derived, this derived by h, simply minus 3. It's simply minus 3 because L derivative by h is 0, minus 3h derivative by h is minus 3. It's a linear expression. this expression derived by h is simply minus 3. So of course now we can simplify it a little bit. 2l squared minus 6hl plus 6hl, see, minus 6hl plus 6hl, they disappear, that's all. Divided by l minus 3h squared. This is the derivative of this function in terms of h. Now, in terms of l, alright, the denominator is the same, l minus 3h squared. Now, the numerator derived by l, 2h, times l minus 3h doesn't change, minus u doesn't change, so it's 2hl multiplied by v derived by l. This v derived by l, 1. So now what do we see here? 2hl minus 2hl. They disappear. 2h times minus 3h is minus 6h squared over l minus 3h squared. So if you have unfamiliar names for variables like u and v, h and l, something and something, it's at the beginning it's a bit difficult not to get confused, and those who have been doing this for your physical lab work or something, I've seen you doing it, know that it's not easy at the beginning. So we are going to practice now, hoping that in the future it might help. Those of you who actually need to do this kind of thing, there are some who do. That's what physics is about. All right, from exercise 1, is there anything else? From exercise 2?
Somehow the powers.
Which one? 61?
61, yeah.
61. xt, xo. How lovely. U in terms of x and t is x times e to the power minus xt squared. Okay, y in terms of x and t is this. So, alright, this will be the quotient rule because it's the product of two functions, 1 and 2. Alright, q derivative by x. Or we could write y derivative. dy by dx, we can write it like this, whichever way you prefer. I'm writing it like this because this is simply, it seems shorter and faster. In many books you will see this kind of notation. Well, I suspect that mostly you will see this kind of notation. So I'm going to put it in somewhere so that you don't forget that it exists, and so that you'll still understand when necessary. Okay? Now, by x, first derived times second. So x derived by x is 1. So the derivative is this. So x derivative is 1 times the second function not derived plus the first function not derived times this second function derived, where x is the variable, t is a constant now. T is a constant now. What is the derivative of the e to the power? First of all, e to the same power always.
Minus 2t squared.
Times minus t squared, but multiplied by. So we could write it's e to the power minus xt squared times 1 minus xt squared. That's interesting. That's a little bit interesting. So I simply simplify this because if we have a habit of leaving these expressions, let's say, wild, then at some moment we will stop understanding what we have been writing. It's always useful to clean it up a little bit. So now derivative by d, obviously time, or we could write dy by dt. Okay, so now in this case x is a constant, so it simply remains there in front of the function, nothing changes. X is a constant now for this. Now, so now we have something in terms of e to the power minus ax squared, right? Something like that to derive. Something like that to derive. I'm not saying that we have that function to derive because then it would be too confusing what is x and what is not x. But e to the power number times x squared. So first of all, it's a composite function. It's a composite function because it's exponential function, but the power of that, the exponent of this exponential function is a function. It's not exactly a variable. So it's basically this. It's basically this. E to the power some function. Now, how do we derive this? I'm not going to do this too much, but I'm simply reminding you of the rules of differentiation.
Yeah.
So this e to the power u derived is e to the power u times u derivative.
Yes.
So in this case, x was the constant. Now e to the power this derived will be e to the same power. Now we have to multiply it by the derivative of this, the exponent.
2t.
Minus 2t, that's all. X, the constant x, the constant x. So now we have minus 2tx squared e to the power minus xt squared. So that would be the combined function. So the first derivative, partial derivative by x, partial derivative by t. Looks like this. That's not too bad. Not too bad. As I said, it takes some practice. It takes some getting used to. It takes some getting used to, especially where the variables have names that are, well, a little bit uncommon. For example, u and v, or instead of z in terms of x and y, we have y in terms of x and t, and so on. Okay, that was 1861. That was 1861. What else do we want? There are lots and lots of interesting functions. I know you don't think them too interesting, not in the way I do, but.
How about 1886?
64 and 86. All right. 64 is sine squared of x plus y minus sine squared x minus sine squared y. Very nice. It is symmetrical with respect to x and y, which means if we do one derivative, the other one should look exactly the same, only with the variables x and y switched. Because it's symmetrical. You see, it doesn't matter if we exchange x and y, the function is the same. So the derivatives, the form of the derivative would be the same, only to the extent of exchanging, as far as exchanging x and y. And this one, 86, is z equals y times e to the power sine pi x y. Ooh, that's something. But remember, pi is a constant always. You don't have to derive by pi. Okay. Derivative, partial derivative by x. Sine squared. Composite function. The derivative of the square is 2 times sine of x plus y, composite function. Now the next function to derive is sine. The derivative of sine is cosine of the same. And finally, times the derivative of the inside in terms of x is 1. Minus sine squared of x. Alright, square derived is 2 sine of x times sine derived is cosine x. Sine squared of y is constant in terms of x, so nothing, 0. So we see that we have 2 sine of x plus y times cosine of x plus y minus 2 sine of x times cosine of x. So what do you think will happen to the derivative in terms of y? Sine squared derived means 2 sine x plus y times sine derived cosine of the same. X plus y derived by y is 1 minus sine squared x derived by y is 0 because it's constant with respect to y, and this minus 2 sine y times cosine y. So we can actually change this. If you remember the formula for the double angle sine, this is sine of 2x. So I can write 2 times sine of 2x plus 2y, double angle, minus, sorry, not 2, it's just sine. Okay, I have to rewrite it. I have to write it's sine of 2x plus y. This is nicer. Sine of double x plus y minus sine of 2x. And this will be sine of double x plus y minus sine of 2y. So 2 sine A cosine A is sine of double angle. That's a very useful formula to keep in mind, not only on paper. But it's also useful to memorize it because we will return to it and we will need it and need it and need it anyway. So we will still have to use it. So that formula is something that should be remembered. Okay, that was 1864. Now 1886. 1886. Okay, can I erase this or?
Yes.
No.
No.
Alright, y times e to the power sine of pi xy. So the partial derivative by x. Partial derivative by x. So y is a constant for this. If we are deriving by x, y is a constant. Because it's a constant multiplied by a function, it remains where it is. Times derivative of exponential function. Again, this. So it's first of all, it's the exponential function as it was, sine pi xy times the derivative of the exponent. The derivative of sine is cosine. So times cosine of pi xy times, because it's a composite function, we now need to derive the pi xy by x. It's pi y. Pi, y, pi. So we have pi y squared cosine pi xy, I'll write it like this, e to the power sine pi xy. I put the brackets there so it's easier to understand. The grouping helps. If you use brackets not to separate things that are obviously well, that are obvious, then at least you might use it for grouping things together so that it's easier to perceive. The perception of this function or the formula is easier if you use some brackets. All right, we still have to derive it by y. dz by dy equals. Now we have a product. So we need to use the product rule again. First function y derived is 1 times the second function not derived is the function as it is, plus first function not derived times this function derived. But we know how to derive this function with a little change. So the derivative of this is the function itself, sine pi xy, times the derivative of sine, which is cosine of pi xy, times the derivative of pi xy by y this time, so it's pi x. So it's pi x. And so we have e to the power sine pi xy times 1 from there, and from this we have y, we have cosine, we have pi x. So I will write plus pi x y times cosine of pi x y. So, and as I said, well, now I'm erasing the previous one. Like this. So again, I took the common factor, the power of e, the exponential function, outside, and I simply look at what's remaining inside. So we could say that there might be some similarities, but not too much. There are differences, of course. What's the time? 25 minutes. Okay. Is there anything else, or whatever?
Or maybe we'll do it at home.
85. Y plus logarithm cubed. That's simple.
Can I ask something?
1880? Arc sine of something horrible. Okay, you know how to pick awful functions. You know how to find awful functions.
In this one.
One question.
Yes.
At 1882, the very last symbol, what is it?
1 minus z to the power square root of t.
Square root of t.
That's square root of t.
And in 69 also, what is
And in 69, it's arctangent. Oh, I have cut something off. It's arctangent of y over 1 plus x squared. So in 1869, I have accidentally cut off part of that arctangent of y over 1 plus x squared. That's 69. 80 is sine of, lost it, x over square root x squared plus y squared. Oh no. On the other hand, the square root of x squared plus y squared is actually the radius, so x over radius, that would be sine. This should be interesting. 1880. 1880 should be interesting because basically this expression x over the square root of x squared plus y squared is actually, I think, is it cosine of the angle? If I have a point somewhere, so this is the x value, this is the y value, then this is that square root of x squared plus y squared in the right triangle. So x divided by this is actually sine of this angle. And then we have arc sine of that angle. So we might get an expression for this angle by this function.
Let's see.
That's interesting. But okay, let's derive it. Derivative by x. Derivative of a composite function. Chain rule again. Arc sine of something. Okay. Arc sine. 1 over square root of 1 minus this square.
It's minus sine squared.
Now there's something, as I said, you need to find your old paper with the table of all derivatives. Some of you actually took some from me from my last semester leftovers. I remember how you did that in the end of January. Okay, so the derivative of arc sine is 1 over square root of 1 minus x squared. In this case it's this squared. So x squared over x squared plus y squared. Something like this. Times, we will simplify later, of course. We will simplify this. Now, that was the derivative of arc sine times, now we need the derivative of this function. Because it's a quotient, we need to use the quotient rule. So, times the denominator squared, this squared, so x squared plus y squared square root and squared. I'm simply writing it a little bit more slowly. Okay, in the denominator, this derived is 1 times the denominator not derived minus this not derived times that square root derived. The square root, the derivative of the square root is 1 divided by 2 such square roots. But now we have to multiply by the derivative of the inner function. In terms of x, the derivative of this would be 2x. With something. That's something.
Can you promise that we will not have such topic in the test?
Yes.
Okay.
Yes. I'm not going to put too complicated functions in the test. So this is, you see, arc sine is complicated in the sense that it has its derivative is unpleasant enough. 1 over square root of 1 minus u squared is unpleasant enough. But then, if that u expression is extremely unpleasant, that's, no, I'm not going to do that. I'm not going to do that. In the test, my main objective is actually to make sure you understand the idea of partial derivative and its applications. So, no, I'm not putting complicated, terrible functions in the test or in the exam. So, alright, 2 and 2 cancel out. Here, x times x, that will be x squared. Alright. So let's see. 1 over. Now, if I attempt to put these two together on the same line, I would have x squared plus y squared minus x squared. That means I have square root of y squared over x squared plus y squared. So at first I simplify this radical expression, this expression under the radical. Simplifying this, I get this. Now, times, okay, here we have x squared plus y squared, simple, without the root anymore. Here we have, now we should do something about this. If I want to put this expression, so that's algebra. And the problem with advanced mathematics, which is what you are studying, is that you are supposed to be able to manipulate complicated expressions quite fast and quite easily. That might be a problem. So what I'm going to do is, in this case, we have square root minus x squared, because this was on top. So x squared divided by the same square root. So what I'm going to do is I'm going to put these two on the same line. I'm going to take this square root up there. This is already up. It's multiplied by this. So what happens is I need to multiply it by another such root. So this actually becomes square root of x squared plus y squared. It's this. When I multiply this by the same root, it's x squared plus y squared. X squared plus y squared. This multiplied by this to put it up. Minus, and we have x squared there already. Minus x squared already. So now we have to try and see what's going on there. So here we have simply y squared on top. It's this part, it's this. Now divided by the square root, I'm putting it already down there, below the line. X squared plus y squared. It's this. So right now I have only written this part. This part comes here. Now of course I still have x squared plus y squared, this down there. Right. And I still have this y squared over x squared plus y squared under the root. Now let's see what's going on there. Something very nice. In fact, if you look at these two square roots together,
Cancel out.
these cancel out, you get the square root of y squared, which is y. So we can see that these two, under the root both, they are both under the root, so cancel out easily. Square root of y squared is simply y. So we have y squared divided by y times x squared plus y squared, which is y divided by x squared plus y squared. Turned out to be quite simple in the end. Although, of course, the process was not so simple. The process to obtain that final answer. So, yes, you do need to practice manipulating expressions. You never know when you might need that. I may not put such awful expressions in the test, but you still need to be able to make sense of this. Make sense in the sense, right? Make sense in the sense that you understand how to combine terms, how to make things simpler, how to put terms on the same line, the same denominator, how to divide a fraction by an expression. This doesn't go up. This stays down there because it's not a fraction. You don't divide by a portion there, so you don't need a reciprocal, and so on. You think we need to derive by y?
No.
No. No.
We get the idea.
You get the idea, yeah. It's well, it's not simple, but it can be fun. And then the crazy woman, her idea of fun. Right. Okay. Perhaps we should look at some implicit, one or two implicit functions.
What will you do for the next time?
Next time.
And what will you do?
Next time we are going to look at differentiation of composite functions in two variables. This was just direct differentiation, direct derivatives. I'm not expecting you to do absolutely everything, all these exercises, but I am sending you the answers to these. I'm sending you the answers to these. Those answers are taken from the back of the same book, so they will be from the book. But so if there's a mistake, an error in that book, then, well, what can I do? I apologize for the authors. But basically, have a look at these. Try to do at least some of them for practice, because we don't have time to do them all in class. But implicit functions, there's something, well, probably we need to look at some implicit functions again to get the idea. So, 19 which? 94. Okay. X e to the power y plus y e to the power x plus z e to the power x equals a. Actually, this is not a very bad implicit function. It is possible to derive this as an explicit function. It is possible to express z in terms of x and y, but all right, let's do it as an implicit function. So the function f of x, y, z would be this minus a, but a is a constant, so the derivative of a does not need to be taken into account. So anyway, okay, I'll write x e to the power y, y e to the power x, z e to the power x minus a. Because this is a constant, it will not appear in any of the derivatives. So f derivative by x, this is a constant, so x times 5 derived is just 5 e to the power y. Y is a constant, e to the power derived is e to the power x. So it's still y e to the power x. Here, z is a constant, exponential function derived is exponential function itself, plus z e to the power x. So this was easy. By y, x is a constant, derivative of exponential function is exponential function. X is a constant, so this is a constant, x to the power e to the power x is a constant, y derived by y is e to the power x. Constant, nothing, no y in there. And finally, f derivative by z. This is a constant for z, nothing. This is a constant for z, nothing. This e to the power x. That's all. So the derivative of z by x, remember, minus f derivative by x, it's this, divided by e to the power x. We can actually simplify this. We could actually simplify this. It's minus e to the power y minus x plus y plus z. By the way, so do you get this part? Divide, and if I divide two powers to the same base, I have to subtract the exponents, one of the exponent laws. Alright, and the derivative by y is x, x e to the power y plus e to the power x, minus in front, of course, divided by e to the power x. So it will be minus x e to the power y minus x plus 1. Just like that. Just like that. So it's not so awful always. Now you have quite a lot of nice things to do. Revise derivatives, basic functions, chain rule, quotient rule, product rule, chain rule, more and more, and so on. So that was 1904. Anything else? 6? Natural logarithm there. Perhaps we might look at 6, although again it shouldn't be very difficult. So ln of x plus z minus xy over z minus 3. I will write it like this already, x, y, z. I already am writing it as expression f equals 0. Here also, if we want to define it as a function implicitly, we have to write equal 0. Okay, derivative by x. Derivative of logarithm, 1 over x plus z. We should multiply by the derivative of x plus z, but that's 1. Remember, when you derive ln of x plus 3, it's 1 over x plus 3. When you integrate this, it's ln of x plus 3. Minus divided by x, it's just y over z. Not bad. Derivative, partial derivative by y. This is a constant for y. There's no y in this logarithm, so it's a constant. Derivative is 0. Derive this by y, it's minus x over z. Again, simple. And finally, the derivative by z, 1 over x plus z, similar to this. Now, this, it's xy constant times 1 over z.
Z minus
1 over z to the power minus 1.
Yeah.
So it's minus 1 z to the power minus 2. Because it was minus, it becomes plus. Xy was there as a constant, and here we have z squared. Okay, so now, formally speaking, we should simplify this and this in order to simplify later on. But, alright, z derivative by x. It's this, so it's minus 1 over x plus z minus y over z divided by minus x, this. Divided by 1 over x plus z plus xy over z squared. I don't like this. It looks like skyscraper, 4-story building or four-layer wedding cake or something terrible. I don't like wedding cakes. Yes. We could multiply
Each other.
We could multiply both the denominator and numerator by x plus z and by z squared, at least to simplify this. So if I multiply, okay, all right, that's algebra. I can leave it for you to play with.
Shouldn't 1x plus z on the denominator and so on cancel each other out?
No.
No?
No.
Why not?
No. That's like pulling legs off a fly.
Why not?
No, it's a bit like, okay, a squared plus 2a divided by a minus 2. Some people try to do it like this. They try to do it like this. And that's like pulling legs off a fly, honestly. That's horrible.
But there's a...
It's like poor fly. Why are you pulling its legs off? You cannot cancel out terms. You can only cancel out factors and coefficients, but they are not factors. You see, they are added to the rest of it. They are not multiplied by it. So what we can do, we can multiply this and this by x plus z. So this becomes 1, this becomes 1, and this becomes something else and something else. A little bit more pleasant, perhaps. So we can try, of course. So if I multiply by x plus z, multiply everything by x plus z. If I multiply this, it becomes 1. If I multiply this, it becomes, that's minus y times x plus z over z. A little bit better, not much. Multiply this by x plus z, it's 1. Multiply this, it's xy, x plus z over z squared. Well, now I can multiply both parts again by z squared to get rid of this. So I have minus multiply by z squared, multiply by z squared, we get y times z plus z squared plus x times y times x plus z. Okay. Not very bad, not very horrible. So it's just that it's a bit messy. It takes, again, it needs care, actually. It's not very difficult to do if you remember the transformations from 7th, 8th, 9th grade algebra, but have to be careful. People have lost the ability to be careful these days. And the other one, again, it would be this divided by this, minus with opposite sign. So z derivative by y would be minus, this becomes plus, so it would be x over z divided by r x plus z plus xy z squared. I'm not going to transform that. Not going to transform that. Whew. I think that's it. So try to do what you can. Try to do what you can from this. And next time we talk about